MEI Statistics Minor, Discrete Random Variables 3, Binomial Distribution. This is the final video, Poisson approximation to the binomial. So, when are the Poisson binomial distributions similar? So here in GeoGebra we have two distributions. The blue is a binomial distribution with n trials and p probability of success on these sliders, and we have a Poisson distribution in red with lambda of 5, and that is calculated so that these both have the same mean. So we recall that the mean of a binomial is NP, so that is going to be equal to 5. Now you can see it's quite a good approximation at the current levels, n equals 50, p equals 0.1. If I then make n smaller, you can see that the errors are creeping up. They're a bit bigger. In fact, there's a fair bit of error now on this bar, a lot more than there was before. If I make n bigger, then that error actually gets smoothed out. So the biggest error there is there, which isn't a huge amount. If I put it back to 50 and then put the probability up to 0.5, you can see that the error bars are considerably bigger. And if I make it smaller, the error bars get ever bigger. If I make it bigger, they start to even out, but still it's not a particularly good approximation. If I make p very big, it's a terrible approximation. Not for any value of n are we getting a good approximation. So it seems that the best approximations are when p is small, and in fact the smaller we go, the better the approximation, and when n is big. So we can use the Poisson distribution to approximate the binomial distribution with lambda equal to np, provided n is large, p is small. The larger n is and the smaller p is, the better the approximation. These criteria seem quite vague, and they relate more to the days of tables. When n was large, you couldn't find a binomial table for the value of n, but if np was fairly small, you could find a table for Poisson. Now, the approximations aren't formally included in the spec anymore, but you may feel free to use either distribution as a model if the conditions hold. In this example, 0.5% of articles produced in a factory are known to be faulty. What's the probability that in a random sample of 500 there are precisely 3 faulty articles? So, we know that if x is the number of faulty articles in the sample, we know that x is distributed binomially with 500 trials and probability of success. Here we're considering a success to be a faulty article because we're counting the number of faulty articles. So it's going to be not 0.5, 0.5%, so that's 0.005. Now, if we're doing this with a Poisson distribution, our lambda is going to be equal to np, which is 500 times 0.005, which is 2.5. So x is approximately equal to a new random variable y, which is distributed as a Poisson with 2.5. We're looking for precisely 3 artifacts, so the probability that y equals 3 is equal to e to the minus 2.5 times 2.5 cubed over 3 factorial, which is 0.214 to 3 significant figures. If we compare that to the actual binomial solution, we remember that it's distributed binomially with 500 trials, 0.005 probability of success, probability that x equals 3, is equal to 500 choose 3 times 0.005 to the 3 times 0.995 to the power of 497. Pop that in the calculator. 0.214 to 3 significant figures. So in actual fact, it is exactly the same to 3 significant figures, a fairly accurate approximation. That's the final video for Discrete Random Variables 3 binomial distribution.